Hello, hello. Welcome to episode 5 of my EE 101 series. Today, as promised, I'm going to talk about Kirchhoff's Voltage Law, or KVL. So let's write this down. EE 101, episode 5, Kirchhoff's Voltage Law, or KVL. To recap a little bit, let me draw the same diagram I drew last time, just to give you this image of the ideal, or rather the general circuit element, just so you're clear on the symbols we're using. So this time I'm going to draw a slightly different circuit, albeit equally as simple as the circuit I used to showcase KCL, or Kirchhoff's current law, except it's set up slightly different. So let me go ahead and do that. Okay, so this time, if you notice, I'm not doing any ellipses off to the sides. I'm not leaving any of the circuit to your imagination. I'm actually drawing a complete circuit here. This is a full loop, and I didn't have to do this. I could draw more to this circuit. I could leave some dots off to the side. I could leave something up to the imagination, but in this case, it's not really necessary. I can draw a complete circuit and fully describe this law, or rather a complete circuit is necessary to fully describe this law, because you need a loop. And so what do I mean by loop? Well, if you remember from the last video, I defined a node, a circuit node, or one of these spots that connects one or more circuit elements via this wire or this line or ideal conductor, as I described in the last video. So this is a loop, because if you pick a node and start there, and then you move through one or more circuit elements from node to node to node, you eventually wind up back at the node you started at. And yeah, I know that seems really obvious. It's a loop, right? But what you'll see moving forward are vastly more complicated circuits, and all you need to understand is when someone says a loop, this is the type of thing they're talking about. So there could be all kinds of other crazy things going on here, but this right here, no matter what else is attached to these nodes hanging off and going in different directions, this is still a loop. And these are still nodes, and it's connecting, these nodes are connecting these circuit elements in this fashion, so this forms a loop. And yes, despite, it doesn't matter how you draw it, this is a node, and this line here, just because it's longer, it's still a node. It's not like it's not a node just because it's an extra long line. And there's no reason I drew it this way. I could have drawn a circuit element here. I could have done more circuit elements. I could have made a much bigger loop. And in reality, I could have drawn just 2 circuit elements. I didn't need a third one, but I think it helps understand a little bit, and it's a little bit too trivial if I just use 2 circuit elements. So without further ado, let me introduce the law itself. KVL says the sum of voltages equals 0 for any closed loop in an electrical circuit. That might sound kind of strange, because if you recall what I talked about in previous videos, every circuit element is going to have a voltage across it by virtue of the fact that there's a current flowing through it. And if there's a voltage across every element, how is the sum going to be equal to 0? And of course, as I'm sure you're probably already imagining, this is something of a semantic rule, similar to KCL. What we're really talking about here is net voltage. and it's with respect to our reference polarities that we assign, just like with the currents. And you'll see how that plays in here. So let me go ahead and define some of these elements. Let me label these. So if I say this is element A, and this is element B, and this is element C. Now next, what I'm going to do is I'm going to assign some voltages to these elements. Much like the example with KCL, we're going to start by just picking the reference polarities. So in real life, when you're doing analysis, you may or may not know the currents. You may or may not know the voltages. If you took a voltmeter, and yes, that's a real thing, a voltmeter. If you took a voltmeter and measured the voltages, then you'd be able to sum them up and see that they equal 0. But in the case of analysis, if you're trying to solve a problem, you might not know the voltages or the currents or some number of voltages or currents. So like the case of the currents, here I'm just going to go ahead and assign some reference polarities, and like the case of the currents, it may or may not turn out that our guess was incorrect, so to speak, and if I assign some polarity to one of these elements, we might find out later that that voltage gives you a negative answer, which what that really means is the voltage that I assigned has the opposite polarity. Now let me dive into this. So let me just go ahead and say that there's a voltage across element A with this polarity, and a voltage across element B with this polarity, and a voltage across element C with this polarity. Now I know I sound like a broken record here, but the next thing you have to do is pick a convention. You're going to pick a direction in which you travel around this loop, and you're going to pick a convention by which you count voltages. So this will work either way, but you have to pick one or the other. So first, you pick a direction that you're going to walk around this loop and start counting voltage. So, and it doesn't matter. So let's just say we're going to go this way, right? So we'll start from a node and move from node to node, counting voltages. So then, let's say I start here on this black dot, and I decide I'm going to move across element B towards this node over here. So the next thing you have to do is say, well, okay, given that element B has this polarity, how am I going to count that voltage? So what I'm doing is I'm moving from the positive side to the negative side of this voltage. And so you have to decide for yourself. As long as you're consistent, it won't matter, but you have to decide for yourself, am I going to count that as a positive? And in general, I think most people do this, so I'm just going to go ahead and do it this way. I count this as a positive. So when I move from this positive terminal to this negative terminal, I'm going to account for this voltage as a positive voltage, right? So VB in this case would be a positive voltage. And then as I move from this node to this node across element C, again, I'm moving from the positive terminal to the negative terminal of element C. So again, I'm going to account for element C's voltage as a positive voltage. But then the interesting thing that you see here is that from this node, as you move across element A, you see there's this minus here. So keeping with our convention, we're going to say that because moving from the positive to the minus, we count this as a positive voltage, then in this case, in the case of element A, as we move from the minus to the positive terminal, we're going to count that as a negative voltage. So now, based on the convention that I chose to apply, let me write this down in an algebraic form. Now recall that in this case, I said VB and VC are positive and VA is negative. So as I write this, VB plus VC, and this is a plus VB plus VC minus VA equals 0. And now realize for a second that if you were to multiply both sides of this equation by -1, it would still be true, right? And what that means is that if I had either used the opposite convention to count voltage, or if I had traveled around this circuit in the opposite direction, I would still get the same answer. And what you're really seeing here is if you solve this equation, you'd wind up with VA equals VB plus VC. And so a really interesting consequence of this analysis is that you see that the voltage across VA is equal to the total voltage that appears across both elements B and C. So if you look at a voltage from the positive terminal of VA to the minus terminal of VA, you see that it's the same voltage as from the positive terminal of VA to the negative terminal of VC. And well, that should be obvious anyway, because these are just directly connected. That's all that's saying. If you look from this node to this node, there's the same voltage from here to here. The only difference is there's one element on this side and there's two elements on this side, but the voltage between these two nodes is the same regardless of which way you look. And so if you think back to my video on voltage and energy and power, where I talked a little bit about a battery and a light bulb, you might imagine that this element A is a source of some kind. And these elements B and C are passive elements, or a load of some kind. They're consuming energy in some way, whereas element A is sourcing energy in some way. You can see how, of course, the total voltage across all these elements, B and C, has to be the same as the voltage across element A. And that's really just the conservation of energy, because all these elements share the same current. And therefore they must share, the source and the load elements must share the same voltage, because all the power that leaves the source has to go somewhere, and all the power that's consumed in these loads had to have come from somewhere. None of it's lost in this ideal system because we have perfect conductors connecting these elements. And so really, just like how Kirchhoff's current law was fundamentally based on the conservation of charge, Kirchhoff's voltage law is really just an extension of the conservation of energy. Like I talked about in somewhat depth, voltage is a potential energy density. What voltage is really describing is it's keeping track of the energy that's either consumed or supplied by the various circuit elements relative to their current. And again, I'll say it one more time, Kirchhoff's voltage law is the extension of the conservation of energy. And so this, just like KCL, is one of the most powerful circuit analysis tools that you have at your disposal. You will use this every day to analyze the most simple to the most complicated circuits. It's very fundamental, but it will never fail you. And usually you have a choice, depending on your scenario, whether or not you want to employ either KCL or KVL. To be honest, I usually use KCL, but there's some scenarios where you just have to use KVL, where to solve the problem that you're tackling, you need to look at voltage loop analysis, and sometimes you have to use KCL, but a lot of times you have a choice and you just use whichever you're most comfortable with, or whichever becomes most convenient for you to write down, or whichever you think is most intuitive to think about. But they really go hand in hand, and so you need to remember both of these. They're bafflingly simple if you really grasp what's going on, but you need to get a lot of practice, because this is your bread and butter. And so with that, I think I'm going to end the video here. Maybe the next video I'll start doing examples. I need to think ahead. I might do some circuit examples. I might start talking about parallel and series circuits. I might start introducing circuit elements. I'm not exactly sure what I'm going to do yet, but those are some potential next videos. So I hope this was helpful. Let me know if there's anything that's unclear, or how I can improve these videos in style or content. And yeah, thanks for watching. I hope you get excited for the next one.